In this lesson, we continue learning about the postulates of quantum mechanics. So far, we have explored somewhat in depth the first two postulates of quantum mechanics. Postulate 1 says that there is a function that has all accessible information about a system. Postulate 2 says that there is a Hermitian operator that corresponds to every dynamical property of the system. We also learned the rules for constructing these operators. Now we move on to postulate 3, which tells us what the possible outcomes are if we try to measure these properties. Later, we'll look at postulate 4, which tells us how to calculate probability for the possible outcomes. So for now, let's focus on postulate 3. Postulate 3 says that if a dynamical property of a system is measured, the only possible outcomes are the eigenvalues of the operator that corresponds to that property. Example, suppose functions f sub 0, f sub 1, f sub 2, and so on are eigenfunctions of operator A, such that if we apply operator A on function f sub j, we get back f sub j times a constant given by j times j plus 1 times b. Here, b is a constant and j is also a constant. But j is restricted to values of 0, 1, 2, 3, and so on. So we can say that j times j plus 1 times b is the eigenvalue that corresponds to eigenfunction f sub j. Is it possible to obtain a value of 4b if we measure a? Based on the information given here, the smallest eigenvalue is when j is equal to 0. If j equals 0, then j plus 1 is 1, and the eigenvalue is 0 times 1 times b, which is 0. This means that it is possible that if we measure a, we could get a value of 0. What's the next smallest eigenvalue? That's when j is equal to 1, which means that j plus 1 is equal to 2. The eigenvalue would be 1 times 2 times b, or 2b. So it is also possible that if we measure a, we could get a value equal to 2b. It should be easy to see that the next lowest allowed value for a is 6b. That's when j equals 2. 2 times 3 times b is 6b. Therefore, we conclude that 4b is not allowed. It's not one of the allowed eigenvalues of operator A. The probability that we would get a value of 4b if we measure A is 0. But what is the probability that we would get any one of the allowed values? To answer this question, we need postulate 4. But before we tackle postulate 4, we'll go over some ideas and terminologies that are used in postulate 4. One of the assumptions in postulate 4 is that a Hermitian operator that corresponds to a dynamical property has an orthonormal set of eigenfunctions. So let's first understand what orthonormal means. A set of functions is said to be orthonormal if every function in the set is normalized, and each one is orthogonal to any one of the other functions in the set. What does it mean when we say that a function, let's say f sub j, is normalized? It's the same meaning when we talked about the state function being normalized. It means that if we multiply f sub j by its complex conjugate, f sub j star, then integrate over all space, we get a 1. In direct bracket notation, we can abbreviate the integral this way. We put f sub j inside both the bra and the ket operators, with no operator in between the bra and the ket. If we have a set of functions and name them f sub 1, f sub 2, f sub 3, and so on, then we can abbreviate even more. If we are referring to function f sub j, we just put j itself inside both the bra and ket operators. So, what does orthogonal mean? When we say orthogonal, we are referring to two different functions in the set. Let's say f sub I and f sub j. When can we say these two functions are orthogonal? If we take f sub j, then multiply it by the complex conjugate of f sub I, then integrate over all space, we get 0 if the two functions are orthogonal. In Dirac bracket notation, we write it like this. We put f sub I in the bra and f sub j in the ket. Or we can just put I in the bra and j in the ket if we have established the context that I and j represent the numbers associated with the set of functions. What if we switch f sub I and f sub j? Remember that if we switch the functions in the bra and ket, the result is just the complex conjugate of the original. But in this case, the original is 0, which is a real number. The complex conjugate of 0 is itself. So it doesn't matter which order you put the functions in the integral. Here's a more compact way of saying that a set of functions is orthonormal. We say that the integral of f sub I star times f sub j over all space is equal to delta ij. This symbol here, lowercase delta with subscripts I, comma j, is called the Kronecker delta. It is equal to 1 if I and j are equal, which means we are referring to the same function. This is the normalization condition. Otherwise, it is equal to 0. If I and j are not equal, we are referring to two different functions. This is the orthogonality condition. Suppose the set of functions g sub 1, g sub 2, and so on is an orthonormal set. Which of these integrals written in Dirac bracket notation is equal to 1? Choice A means the integral of g1 star times g2 over all space. Since the functions are not the same, the integral is 0. We say that g1 and g2 are orthogonal to each other. Choice B means the integral of g3 star times g3 over all space. Since the same function g3 is used in the integral is equal to 1. We say that the function g3 is normalized. We're given that it's part of the orthonormal set. One of the assumptions in postulate 4 is that a Hermitian operator that corresponds to a dynamical property has a complete orthonormal set of eigenfunctions. We already know what orthonormal means. What do we mean by a complete set? We say that a set is complete if we can write any function that obeys the same boundary conditions as a linear combination of functions in the set. Let's say the functions f1, f2, and so on form a complete set. Then, if some function g obeys the same boundary conditions as the function in the set, we can write g as a linear combination of these functions. We can say that g is equal to c1 times f1 plus c2 times f2 plus c3 times f3, and so on. Here, c1, c2, c3, and so on are constants. If the set is orthonormal, we can actually show that the coefficient for function f sub I is just the integral of f sub I star times g over all space. And it can also be shown that the integral of g star times g is equal to the sum of the squares of the absolute values of the coefficients. We'll talk about boundary conditions some other time when we deal with specific systems. For now, let's take a look at a simple example to illustrate what we mean by a complete set. Suppose the set of functions f1, f2, and so on is a complete orthonormal set, and function g can be written as 2 times f1 plus 3 times f2. What is the value of the integral f2 star times g over all space? This integral is just the formula for the coefficient of f2 in the expansion of g. So the answer is the coefficient of f2, which is 3. Let's verify. We substitute 2f1 plus 3f2 for g in the integral. We can distribute f2 star and break up the integral into a sum of two integrals. We get integral of f2 star times 2f1 plus the integral of f2 star times 3f2. We can pull out the constant from each of these integrals and we get this. Note that the integral of f2 star times f1 is equal to 0 since f2 and f1 are orthogonal to each other. Any two functions in the set are orthogonal to each other. And the integral of f2 star times f2 is equal to 1 since all the functions in the set are normalized. So the answer is 3, which is the coefficient of f2. Let's see how we can work this out using Dirac bracket notation. We write f2 in the bra and g in the ket. We substitute 2f1 plus 3f2 for g. We distribute the bra operator on the linear combination of f1 and f2. We pull out the constants from the bracket. Then we see that the first term here is 0 because f2 and f1 are orthogonal. And the second term is equal to 3 because f2 is normalized. Suppose the set of functions f1, f2, and so on is a complete orthonormal set, and the function g can be written as 2 times f1 plus 3 times f2. What is the value of the integral g star g over all space? Here's what we do. We just take the square of the absolute value of each coefficient in the expansion, then add them all up. The coefficient of f1 is 2, and the coefficient of f2 is 3. 2 squared plus 3 squared is equal to 13. Is function g normalized? The answer is no, because the value of the integral of g star g is not equal to 1. Can we normalize g? Yes, it's quite easy. We just multiply it by a normalization constant. Let g sub n be the normalized version of g. Then g sub n is just g times the normalization constant n. Since g sub n is normalized, the integral of g sub n star times g sub n over all space is equal to 1. Substituting ng for g sub n and solving for n, we find that the absolute value of n is just equal to 1 over the square root of the integral of g star g. So the absolute value of the normalization constant is 1 over square root of 13. So now we are ready for postulate 4. Postulate 4 assumes that an operator that corresponds to a dynamical property has a complete set of orthonormal eigenfunctions. Suppose the eigenfunctions for operator A are f1, f2, f3, and so on, and the corresponding eigenvalues are a1, a2, a3, and so on. Then we can write the state function psi as a linear combination of the eigenfunctions. And the probability of obtaining the eigenvalue a sub I is equal to the square of the absolute value of coefficient c sub I. For example, the postulate is saying that if we apply operator A on function f2, we get a constant times f2. That constant is a2. If we take the integral of f2 star times psi over all space, the number we get is the coefficient of f2, which is c2. If we were to measure property A, the probability that we would get a2 is the square of the absolute value of the coefficient of f2. That's the absolute value of c2 squared. What is the probability of obtaining a value of 2.5 omega for property A if it's measured, given that A hat applied on eigenfunction g sub v yields v plus 1/2 times omega times g sub v, where omega is a constant and values of v are restricted to 0, 1, 2, and so on. And psi happens to be 1 over square root of 6 times g1 minus 2g2 plus g3. We can see that the formula for the eigenvalues is v plus 1/2 times omega. A value of 2.5 omega corresponds to the eigenvalue when v is equal to 2. 2 plus 1/2 is 2.5. So we are interested in the probability of getting the eigenvalue of function g2, which means that we need the coefficient of g2, which is -2 times 1 over the square root of 6. Therefore, the probability of getting a value of 2.5 omega for A is equal to the square of negative 2 over square root of 6, or 4 over 6, or 2/3. You should be able to show that the probability of getting 1.5 omega is 1/6, and the probability of getting 3.5 omega is also 1/6. The probability of getting anything else would be 0. All the probabilities should add up to 1. If they don't, that means that the wave function as written isn't normalized properly and you have to fix it. In the preceding example, we saw that because psi only has contributions from eigenfunctions g1, g2, and g3, we can expect to get only 3 of the many possible values of property A if we try to measure it. These are 1.5 omega with a probability of 1/6, 2.5 omega with a probability of 2/3, and 3.5 omega with a probability of 1/6. This means that we can have two systems with the same psi, two systems in the same state, but we could get different results if A is measured. If we imagine a very large number of systems, all with this same psi, and we measure A for all of them, we expect that 1/6 of these systems will give us A equals 1.5 omega. 2/3 will give us 2.5 omega. And the remaining 1/6 will give us 3.5 omega. We can calculate the average by multiplying each possible outcome by the probability of the outcome, then adding up the results. We multiply 1.5 omega by the probability that we would get it, which is 1/6. We multiply 2.5 omega by the probability that we would get it, which is 2/3. We multiply 3.5 omega by the probability that we would get it, which is 1/6. Then we add everything up and we get 2.5 omega. This average value is also known as the expectation value. It should be relatively easy to show that the integral of psi star psi over all space is equal to the sum of each possible outcome multiplied by the probability of each outcome. Remember that the square of the absolute value of the coefficient in the expansion of psi is the probability. In Dirac bracket notation, we can write the expectation value of property A by putting psi in the bra and the ket and putting operator A in between. In a lot of textbooks, you may find the formula for the expectation value written like this. The formula that we wrote earlier is divided by the integral of psi star psi over all space. This just anticipates the possibility that the expression for psi hasn't been normalized. In this case, you can think of the squares of the absolute values of the coefficients as relative probabilities. If each of these relative probabilities is divided by their sum, then you get the actual probabilities. Note that if psi is normalized, then the denominators here will be equal to 1. This definition of expectation value is often given as a postulate instead of our postulate 4. You can see that here we derived it from our postulate 4. Both statements are equivalent. Suppose eigenfunctions f1 and f2 of the B operator have eigenvalues of 2 and 4. And the wave function for the system happens to be 1 over square root of 2 times f1 plus f2. What is the probability of getting a 2? Both eigenfunctions have the same coefficient in the expansion of psi. So we know that the probability of getting each of the two possible outcomes is the same, 50%. Consider the case where you measured B and found it to be 2. What would you get if you measured it again? The answer is that it would still be 2, as long as during the time between the measurements the system has not interacted with anything else in the universe. The act of measurement changes the wave function. We say that it reduces the wave function into an eigenfunction of the property you measured. So, postulate 3 says that the next time you make a measurement, there will now only be one possible outcome. For a more interesting version of this question, look up Schrödinger's cat. You should be able to find a lot of videos on YouTube about it. In an earlier lesson, you were told that the square of the absolute value of the wave function is interpreted as a probability density function for locating particles. This is known as the Born postulate. We are not giving this postulate a number as it is actually implied in our postulate 4. Let's take a look at the expectation value for the location of a particle along the x-axis. Based on postulate 4, the formula would be integral over all space of psi star times x hat applied on psi. But x hat is just a multiplicative operator, so we can also write the integral as integral of psi star times x times psi. Note that here we've replaced our abbreviation of the integration variable. We now explicitly specify that we are integrating with respect to x from negative infinity to infinity. Since multiplication is commutative, we can switch x and psi star. This formula says that to get the average x, multiply each possible value of x by psi star psi dx, then add up everything. Remember that integration is essentially a summation over infinitesimally small intervals. Therefore, psi star psi dx must be the probability of finding the particle between x and x plus dx, and psi star psi is the probability density. We cannot associate an actual probability for a continuous variable like x. Instead, we have a probability density function.